Good morning everyone. So welcome to my YouTube channel Avatarm. Today we are going to see sixth set on uniform convergence of function. This is a problem set. So till now, if you have not subscribed my YouTube channel, subscribe it for latest news of competitive exam like CSIR, NET, JET, NBHM, CMI, TFR, all these high level competitive exam. I am doing this question keeping point of view of these exams. Okay, so let's start today's session now. So first question is let Fn I to R be a uniformly continuous function for each n belongs to n, and Fn converging to F uniformly on I. Then option number 1 is F is uniformly continuous on I. F need not be uniformly continuous on I. Option number C, F is continuous but need not be uniformly continuous on I. Option number 4 is F is not continuous on I. Okay. So let's see. So Fn converging to F uniformly on I. Okay. Let epsilon greater than 0. Then there exists capital N belongs to N such that Fn x minus Fx is less than epsilon by 3 for all n greater than capital N and x belongs to I. Okay. If we take put n is equal to capital N, then still the statement is true because you can take n greater than equal to n. You can take n is equal to capital N also. So F n x minus F x less than epsilon by 3 for all n greater than capital N. Sorry, x belongs to I. This is equation number 1. Okay. Since Fn is uniformly continuous on I, we have there exists delta greater than 0 such that Fn x1 minus Fn x2 is less than epsilon by 3 for all x1, x2 belongs to I such that x1 minus x2 difference is less than delta. Okay, less than delta. Let's say it equation number 2. Okay. Next, let x1, x2 belongs to I with x1 minus x2 delta less than delta. Then by equations 1 and 2, we have what we have. We are taking fx1 minus fx2. I can subtract. Okay. Okay. I can add and subtract fn x1 and fn x2. Okay. Using triangular inequality, we have Okay, by equation number 1, it is less than epsilon by 3. By equation number 1, again, it is less than epsilon by 3. By equation number 2, it is less than epsilon by 3. So what we have? We have, this is epsilon by 3. That is epsilon. Okay. This implies fx1 minus fx2 less than epsilon for all and for all x1, x2 belongs to I with x1 minus x2 less than delta. Okay. What does it mean? F is uniformly continuous on I. Okay. It means F is uniformly continuous on I. So which option is correct? Option number 1 is F is uniformly continuous on I. So first option is correct. Okay. F need not be uniformly continuous. Other options are not correct. Okay. Because every uniformly continuous and is continuous and uniform limit of continuous function is continuous. So option number D is not correct. C is not correct because it is uniformly continuous. And D is also not correct. So option number A is correct. F is uniformly continuous on I. Okay. We have verified it. Now you see this option. F and B monotonically increasing functions. F and converging to F uniformly. Right, then what will be? First option is given F is not monotonically increased. Second option is given F is monotonically increasing. C option is given F is monotonically increasing. D is neither monotonically increasing nor monotonically decreasing. Okay. So Fn is monotonically increasing. Okay. And Fn converging to F uniformly. If it is converging uniformly, this implies Fnx converging to Fx for each x belongs to I, because once a function is sequence of function is uniformly convergent, it is pointwise convergent also. Okay. Now since Fn is monotonically increasing, for fix x belongs to I, we have Fn plus 1 x is greater than Fn x for all n belongs to n. Okay. 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 Which Fn is, sorry, 1 minute. I have made a mistake. Each Fn is monotonically increasing, sorry. For n belongs to n, Fn is monotonically increasing. Each Fn is monotonically increasing. It is not given that sequence is pointwise monotonically increasing. Okay. It is pointwise. Each Fn is monotonically increasing. Okay. So Fn is monotonically increasing. What does it mean? It means what do we have? Since Fn is monotonically increasing, we have Fn x2 is greater than equal to Fx1 for all x1, x2 belongs to I with x2 greater than x1. Okay. Now letting here is n. Letting n tending to infinity, we get letting n tending to infinity, we have what will have? Where it will converge? It will converge to fx2. It will converge to fx2. It will converge to fx1, and this will hold. Okay. Okay. So what does it mean? For all x1, x2 belongs to I with x2 greater than x1. What does it mean? It means that f is monotonically increasing. This implies f is monotonically increasing. So which option is correct? Option number A is not correct. Option number B is not correct. Option number C is correct. Okay. Option number D is also not correct. Okay. F is monotonically increasing. Now, question number 3, you see, A, B are real numbers such that A is strictly less than B, and each Fn on A, B be a function of bounded variation. Okay. If Fn converging to F uniformly on AB, then option number B, F is function of bounded variation on AB. F need not be function of bounded variation on AB. F is function of bounded variation on AB, provided each Fn is continuous. F is not function of bounded variation on AB, even if each Fn is monotone on AB. Okay, let's see this question. Okay, so let's define Fx is equal to x sine phi upon x if x is x belongs to open interval 0, 1. Open interval open 0, close 1, and 0 if x is equal to 0. Then f is continuous on close interval 0, 1. Okay. Now by Weierstrass approximation theorem, by Weierstrass approximation theorem. Now f is continuous, and also f is not function of bounded variation on AB. Sorry, close interval 0, 1. This is a standard example. We have this function that is continuous and it is not a function of bounded variation. It is a standard example. You can check it that this function is continuous on closed interval and it is not a function of bounded variation. Now by Weierstrass approximation theorem, there exists sequence of polynomials Pn such that Pn converging to F uniformly on closed interval 0, 1. We have seen Weierstrass approximation theorem. I have made a separate lecture on this Weierstrass approximation theorem that has title of Weierstrass approximation theorem. You can see my playlist Uniform Convergence of Function. You will find a lecture Weierstrass approximation theorem. Okay. We know that polynomials are functions of bounded variation. Polynomials on closed intervals, closed and bounded intervals are of bounded variation. Each polynomial is function of bounded variation on any closed and bounded interval. So this implies Pn is function of bounded variation Polynomials are always functions of bounded variation on closed interval. On closed interval 0, f is not function of bounded variation. Okay, bounded variation. But Fn converging to F uniformly on closed interval 0, 1. So uniform limit of functions of bounded variation need not be bounded function of bounded variation. We have seen this in this example. So which option is correct? F is function of bounded variation. This is not correct. Because uniform limit of functions of bounded variation need not be of bounded variation. F need not be function of bounded variation on, yeah, this is correct. F is function of bounded variation on AB provided each of n is continuous. You see that polynomials are continuous. Still, F is not function of bounded variation. This is not. F is not function of bounded variation on AB even if Fn is monotone. If Fn is monotonically increasing or decreasing accordingly, then F is monotonically increasing and decreasing accordingly. And we know that monotonically increasing functions or decreasing functions are always functions of bounded variation. So this option is also not correct. Okay. So option number B is correct. Now see, move to option question number 4. Okay. Let AB belongs to R such that A is strictly B. If Fn belongs to LP for 1, P lies in between 1 and P, it can take value P and 1. P can take value 1 and infinity also. Such that Fn converging to F uniformly on closed interval AB. Then F does not belongs to LP. F belongs to LP. F is option number 3 is F is continuous and D is none of the above. Okay. So let's see this example. So Fn converging to F uniformly. Okay. Let epsilon is 1. Then there exists n belongs to n such that Fn x minus fx is less than 1 for all n greater than capital N and x belongs to closed interval AB. Okay. Now this statement is also true. Put n is equal to capital N. Still this statement is true. We have capital N for all x belongs to closed interval A. Okay. Now, what does it mean? Now you see that now what is this? A to B f n x minus fx p dx. This will be less than, because it is bounded by 1, a to b 1 dx. So what is this? This is b minus a. That is finite. Okay. This implies f n minus f belongs to LP. Okay. Since, okay, so fn minus this belongs to LP. But now, since fn belongs to LP AB and fn minus f belongs to LP AB, also LP AB is a vector space. We have fn minus f will also belongs to LP AB. And what is this quantity? This is nothing but f. So f belongs to, so this implies f belongs to LP AB. Okay. So f belongs to LP. Okay. You can deal this case p less than infinity. Okay. For p is equal to infinity, you can check also. That is obvious. Okay. Because fn minus f capital N minus f will be bounded, and fn is also bounded. Difference will be bounded. So it will belongs to L infinity. You can check separately. I have checked it for p greater than equal to 1 and s to be less than infinity. So option number B is correct. Okay. Now see this option. Fn belongs to LP, then converging uniformly. Okay. Now you see that I'm taking R in place of R. Suppose I'm taking this case. Okay. Okay. Now I'm taking this function. I'm taking fx is equal to x upon 2x 1 plus x square. That belongs to C naught R. And we know that CCR is dense in C naught R. Okay. So what does it mean? What is the meaning of this? It means, because this f belongs to C naught R, this implies there exists fn sequence of C in CCR such that fn converging to f uniformly. Okay, uniformly. We know that CCR functions are also LP. CCR functions are, CCR is contained in LPR. Okay, containing LPR. Now, so Fn belongs to LPR for each n belongs to n, n belongs to capital N, which belongs to capital N. Okay, and Fn converging to F uniformly. F converging to F uniformly. Now you see that whether this in place of this function you can take absolute value here. Okay, still it belongs to F C naught R. Okay, now okay, you check integral of this function minus infinity to infinity fx dx. What is this? Because function is even, I can take 2 times. Okay, what is this? 2. Okay, so what is this integral? Limit delta tends to 0, 0 to delta tends to infinity to, because I can skip the mod. Okay. What is this? What is this? This is log. This is log limit delta tends to infinity. This is log 1 plus x square. Okay. 0 to delta. So 2 limit delta tends to infinity. What is this? Log 1 plus delta minus log 1. 1 plus 0. Log 1 and 1 plus 0 means log 1. Log 1 value is 0. So limit. What is the value of this? When delta tends to it is infinity. So what does it mean? What we have? We have minus r, minus infinity to infinity, minus infinity to infinity. Okay. Fx dx is infinity. It means f does not belongs to L1R. Now what you will do, I have checked it for p is equal to 1. Similarly, what you will do, you can take power here, you can for verify for each p, you can take power, whole power 1 by p, and still there will be some function CCR which will converge, then you will find it will work for p, any p in between 1 and less than infinity. Okay, I have checked for p is equal to 1. You can modify this f by taking power p 1 by p. Okay, still it will work. So it means this implies Fn converging to F uniformly. Each Fn is LP R. F does not belong to LP R. Or I am taking p less than infinity. Okay. Now, if we take p is equal to infinity, now if we are taking case p is equal to infinity separately, if we are taking case p is equal to infinity separately, then what will happen? If we are taking p is equal to infinity, after you take epsilon is equal to 1, you will find fn x minus fx less than equal to 1. Okay. For some, there exists capital N. Okay. Belongs to N. Now, Now Fn belongs to L infinity. Okay, and this implies Fn minus F belongs to L infinity. L infinity is vector space, so their difference will belongs to. Okay, so this implies because L infinity is a vector space, then F is equal to F minus Fn minus F belongs to L infinity. So which option is correct? F is always in LP. It is not correct. Will not be in LP. Okay, this option is correct. When F belongs to L infinity for P is equal to infinity, this option is also correct. Finally, this option is correct because it contains P and C. Okay. Okay. So erase this one. Option number D is correct. Okay. So we have done this question also. Okay. So we have completed this set. So if you have any problem and issue related to this set, okay, so you can comment me on my YouTube channel. So thank you for today's session. Like, share, comment and subscribe my YouTube channel for such type of questions. So thank you very much for today's session. Thank you very much. We will see you in next session. Thank you very much.